Good morning all. Now in our previous lecture we discussed the numerical solution of ordinary differential equation part 1. Now we are discussing the numerical solution of differential equation part 2. In the previous part we are discussing Euler's method. We will go to method of order 2 and order 4. Now we will discuss finite difference method. So the finite difference method, which is also known as net method, is a popular method for solving boundary value problems. In this method, the derivatives are replaced by finite difference relations and then involving the resulting system of equations by a standard procedure. In general, for better accuracy, central differences are preferred to replace the derivatives. So in this method consist of n plus 1 points, and in numericals we are always considering n plus 1 points, and we are dividing the interval x0 to xn into n number of subintervals at the point x1, x2, x3 up to xn minus 1, such that xi equals to x0 plus I equals to 1 to up to n. We know this. Then the corresponding values of y at these points are denoted by yi equals to f of xi. So actually we are taking n plus 1 points and the corresponding functional values, and let the differential equation, that boundary value problem, we assume it f1x y double dash f2x y dash f3x y equals to rx. That means second order derivative, first order derivative, and f3y equals to rx. Next, our boundary conditions, y of x0 equals to y0, y of xn equals to yn. Always I said that if our differential equation is dy dx equals to f of xy, then our initial value is x0 and last value is xn. So y of x0 equals to y0 and y of xn equals to yn. So if our functions defined at the starting value and the ending point, so this is boundary value problem. So our required solution is yxr r from 1 to 3 up to n minus 1. Now we have to discretize the equation 1 sign in satisfied by xi yi. We assume that equation 1, this is our equation 1, that BVP, f1x double derivative of y, f2x first derivative of y, f3x y equals to rx. So first we satisfy this equation by xi yi. That is f1 xi equal into yi double dash f2 xi yi dash f3 xi yi equals to rxi. Now by Taylor series we have y of xi plus h equals to y xi plus h y dash xi plus h square 2 factorial y double dash xi h cube 3 factorial y triple dash xi, like this way. And y xi minus h, again by using Taylor's formula, y xi minus h y dash xi h square by 2 factorial y double dash xi h cube by 3 factorial y triple dash xi, alternative sign. So we are using the Taylor series formula for y xi plus h and y xi minus h. Now we are subtracting 3 and 4, adding 3 and 4. When we are subtracting y xi plus h minus y xi minus h equals to 2h y dash xi, 2h y dash xi. So from here we can calculate y dash xi, that means first order derivative, plus this y of xi plus h minus y of xi minus h by 2h, order of h square. So yi dash equals to yi plus 1 minus yi minus 1 by 2h. Then when we are adding 3 plus 4, then we have yi plus h plus y of xi minus h, that means 2y of xi plus h square y double dash xi. So y double dash xi equals to y of xi plus h minus 2y xi plus y xi minus h by h square plus order of h square. yi double dash equals to yi plus 1 minus 2yi plus yi minus 1 divided by h square. Submitting the expression for yi dash, yi double dash xi, that means yi double dash, then the equation 2 gives, equation 2 means that BVP, boundary value problem. This is the boundary value problem. We are putting all the values of first order derivative and second order derivative. We are getting this value. We are getting this is as our differential equation, and we are simplifying it. After simplifying, we are assuming these three yi minus 1, and we are taking common yi minus 1. We are getting one functions in bracket, and again we are taking common yi, and we are getting these values, and we are taking common yi plus 1. We are getting, then the right hand side is 2a square r yi I equals to 1 to up to n minus 1. So that equation 6 will give n minus 1 linear equations. The number of unknowns in these equations are n plus 1, y0, y1, y2 up to yn. The values of two unknowns will be determined by the boundary conditions y of x0 equals to y0 and y of xn equals to y. The numerical values of y0 and yn are known, and raised yn minus 1 unknowns may be obtained by solving n minus 1 equations in 6. So this is the finite difference method. Now we solve this problem by using finite difference method. So this is the equation. Second order derivative is, this is the differential equation. Boundary value problem means d2y, not necessarily, but one differential equation y of x0 equals to y0, y of x0 equals to y0, y of xn equals to yn. Using finite difference method, taking h equals to 0.25. The given equation is approximated by yi plus 1 minus 2yi plus yi minus 1 by h square plus yi equals to 0, I equals to 1 to up to n minus 1. Therefore, yi minus 1 plus h square minus 2yi plus I plus 1 equals to 0, I equals to 1 to up to n minus 1, which together with the boundary equations y of 0 equals to 0, y of n equals to 1, comprise a system of n plus 1 equations for n plus 1 unknowns y0, y1, y2 up to yn. Now we will choose h equals to 0.25, that is n equals to 4. Then the above system becomes y0 minus 1.9375 y1 plus y2 equals to 0, y1 minus 1.9375 y2 plus y4 y3 equals to 0, y2 minus 1.9375 y3 plus y4 equals to 0. Three equations, three unknowns. Unknowns are y0 given, y1, y2, y3, and y0, y4 given because this is BVP. Boundary values are given. So we can easily calculate. We can actually, from the three equations, we can easily find out the three unknowns, and these unknowns are here y0, y4 given. So y1 is 0.2943, y2 is 0.5701, y3 is 0.8108. So this is the value. Actually, you have to, we are starting with 0, h is 0.25, so y0 is 0, y1 is 0.25, y2 is 0.05, and y3 is 0.75, and y4 is 1. This is calculated here. So there is another problem for practicing of my students. Next method is predictor corrector method. In order to solve the differential equation by this method, we first obtain the approximate value of yn plus 1 equals to y of xn plus 1 by predictor formula, and then improve this value by means of a corrector formula. That means first we predict the value of the integration by some formula, then we'll check this value is corrected value or not. So for this reason there is a corrector formula. So for this reason name of this method is predictor corrector method, and it may be noted that corrector formula is more accurate than predictor one, although it requires a companion of predictor formula. Otherwise corrector formula is useless. First, you need that predictor formula. First, you have to predict the value of your solution of the differential equation. Then we apply this corrector formula and we correct it. And also we have the knowledge of initial set of values y0, y1, y2 up to yn, otherwise it is not possible. So for predictor corrector formula, values of x and values of y are known to you. So if for under the predictor corrector banner, there is a method. Name of this method is Milne's method. So this multi-step method due to Milne is obtained by integration moreover over more than one step. Integration of differential equation dy dx equals to fxy over the range xn minus 3 comma xn plus 1 gives yn plus 1 dash over the range xn minus 3 comma xn plus 1 gives yn plus 1 dash equals to yn minus 3 plus integration xn minus 3 xn plus 1 f of xy y f xy equals to dx. So actually this is the differential equation dy dx equals to f of xy over the range xn minus 3 comma xn plus 1 that gives yn plus 1 dash equals to yn minus 3 integration xn minus 3 to xn plus 1 f of xy dx. Now predictor corrector formula evaluating this integral by 3-point Newton Cotes quadrature rule and neglecting the error term, we get yn plus 1 p equals to yn minus 3 plus 4h by 3 2fn minus 2 minus fn minus 1 plus 2fn, that is equation 1, which is the 4-step explicit recursion formula of order 4 known as Milne's corrector formula of order 4. On the other hand, if we integrate the differential equation, that is dy dx equals to f of xy over the range xn minus 1 to xn plus 1, which gives yn plus 1 equals to yn minus 1 plus integration xn minus 1 to xn plus 1 dy f of xy equals to dx. Evaluating this integral by Simpson's one-third rule with interpolating points xn minus 1, xn plus 1 and neglecting the error term, we obtain yn plus 1c, that is the corrector formula, equals to yn minus 1 plus h by 3 f of xn minus 1 plus 4fn plus 2 f of n plus 1. So which is the 4th step implicit recursion formula of order 4 called Milne's corrector formula of order 4. Now predictor formula, compute y of 0.4, compute y of 0.4 by Milne's predictor corrector method from the equation dy dx equals to xy plus y square, given that y of 0 equals to 1, y of 0 equals to 1, y of 0.1 equals to 1.1169, y of 0.2 equals to 1.222773, y of 0.3 equals to 1.5040. Now we have x0 equals to 0, x1 equals to 0.1, x2 equals to 0.2, x3 equals to 0.3 and h equals to 0.1, y0 equals to 1, y1 equals to 1.1169, y2 equals to 1.2273, y3 equals to 1.5040. Also if xy equals to xy plus y square, therefore y of f of 0, f of x0 y0, f of 0, f of x0 y0 equals to 1, f1, f of x1 y1 equals to 1.39, 1.3591, f2 equals to f of x2 y2, that equals to 1.8869, f3, f of x3 y3, like this way. Now putting the value of n equals to 3 in 1 and 2, we get y4p, that means y0 plus 4h by 3, 2f1 minus f2 plus 2f3, And corrector formula y4c equals to y2 plus h by 3 f2 plus 4f3 plus f4. From this previous formula, predictor and corrector formula, this is the predictor formula and this is the corrector formula, and here we are putting n equals to 3. Okay, because this is the integral formula of 3-point Newton Cotes quadrature formula. So we are putting these values in the predictor formula. Next, so from 3 and 4, predictor formula and corrector formula. This is 3 and this is 3 and 4. Predictor formula and corrector formula. So predictor formula, we are putting these values, we are getting this value. Hence functional value f4 p1 comma 1, we are getting 4.0988. Then we are using corrector formula and we are getting these values 1.8386. So y4c1 equals to f of this functional, and we correct that functional value also. Again, this corrector formula and this predictor formula, they are not equal. So again, we have to use corrector formula with the new functional value. We are using that new functional value and we are using that corrector formula. Again, we are using that corrector formula here, and these two corrector formula are not equal. Again, we are using that, again we are improvise our functional value, and that is 4.1142. 1182. Then this is y4c3. Again we are using corrector formula and we are getting these values. These two values are equal, so we can say y of 0.4, that corrector value of 2, this value and this value up to 3 decimal places are equal, so we can say this is the solution of the required integral. And there is a problem for students, you do it yourself. Now again we'll discuss this lecture, what we are doing here. So this is a finite difference method. So here we are discussing how to solve boundary value problem. This is the solution of boundary value problem. This is the BVP that is given here, and these functions are defined at the initial value and the ending values that is already given to us. This is the y of x0 equals to y0, y of xn equals to yn. Now previous BVP, we are satisfying this BVP at the point xi, yi. We are calculating these values. Then we are using Taylor series. With the help of Taylor series, we are finding the value of y xi plus h and y xi minus h, and from this, using addition and subtraction, we are trying to find out the value of first order derivative and second order derivative. Then we are putting these values into our BVP. So we are putting, these are the values, we are putting these values in our BVP, and we are getting a equation, last equation, and this equation is easy to handle, and we are from this equation we are getting n minus 1 linear equations, and the number of unknowns of these equations are n plus 1, where y0 and y1 are given, initial and ending values are given. The values of two unknowns will be determined by the boundary conditions y of x0 equals to y0, y of xn equals to yn. The numerical values of y0 and yn are known, and rest n minus 1 unknowns may be obtained by solving n minus 1 equations in 6. So this is the finite difference method. We solve this differential equation. Solve the differential equation using finite difference method, taking h equals to this. So y of x0 equals to y0, y of xn equals to y. The given equation is approximated by yi plus 1, y minus yi plus yi minus 1 by h square. This equals to 0, yi minus 1. So this is the formula. We are replacing our given differential equation by first order and second order derivative, and we are getting these equation. Now we are simplify these equations, and we are putting the initial value and ending value. Then we are getting this type of system, and in this system 3 values are unknowns, y1, y2 and y3, and we are using the initial conditions and that equations we are finding these values y1, y2, y3, and this is the solution. This is the finite difference method. Now there is another one. This is a problem for students, and there is another one method, predictor-corrector method, that means Milner's method. In this method, we are predict the solution of the differential equation. Then there is another one formula by which we will correct our differential equation. So this is the predictor formula, and this is the 3-point Newton's quadrature rule, and neglecting the error term. This is the predictor formula, and this is the corrector formula, and this is a two-step implicit recursion formula of order 4. So there is a problem. So in predictor-corrector formula, all values to be defined, otherwise we cannot solve it. So these values are given: y of x0, y of x1, y of x2, y of x3. That means we have to find out y of 0.4. All values are given. Values of x0, h, y0, y1 all are given. This is the functional value. So here we can easily calculate f0, f1, f2, f3 like this way. Then this is the formula for predictor. This is the formula for corrector. Then first we plot all these values in the predictor formula. We will get this answer. Then we improvise our functional value. We are getting this value, and then we are getting, using that corrector formula, we are getting the solution. That both the solution, predict value and corrector value, both are not equal. Then we have to again correct our solution. How will we correct it? Again we will improvise our functional value for corrector value, for corrector formula. Then again we use that value in the corrector formula. Then we are getting this value. So previous corrected value and now this corrected value, they are not equal. So again we are trying to find out this functional value. Again we are using that functional value in the corrector formula. Then we are getting these values. Last two corrected values are equal up to 3 decimal places. So we conclude that this is the solution of our differential equation. Now this is the method to solve differential equation. Now thank you.